Mathematician Hermann Weyl said that mathematics is the science of the infinite. It's a reasonable claim, given that infinity is pervasive across all branches of modern mathematics. But it wasn't always this way. We've had a long and tumultuous history trying to get a grip on the slippery concept of infinity. This is a condensed, paradox-filled tour of that history. Perhaps to no surprise, the story begins in ancient Greece with Zeno of Elea. He produced a collection of paradoxes to show that constructing the whole from infinitely many parts leads to absurdities, like motion is impossible. Consider Zeno's dichotomy paradox. Atalanta is at A and wants to get to B. She can approach B by traveling half the distance, and then traveling half the remaining distance, and half the remaining distance, and so on to no end. It's an infinite process with no last step, and since there is no last step, she will never reach B. In an attempt to solve this paradox, Aristotle distinguished between actual infinity and potential infinity. Actual infinity is completed and definite and consists of infinitely many elements. For example, it would apply to a hotel that actually has infinitely many floors. Potential infinity is never complete. Elements can always be added, but never infinitely many. For example, it would apply to a hotel which is continually growing. So we cannot permanently label any floor as the top floor, even though at any moment in time, it always has a finite number of floors, because it has the unbounded potential to grow. And Aristotle's view was that we were using actual infinity when we should have been using potential infinity. We assumed that a line is actually composed of infinitely many points when we should have assumed that we start with a line and that points emerge when a line is cut. And no matter how small the line segments get, they always have the potential to be cut further. By starting with a line instead of points, with a completed journey instead of instants in time, Aristotle concluded that there is no paradox of motion. And with this thinking, Aristotle relegated infinity to a potential. And it stayed that way for more than a millennia. That's not to say that infinity was forgotten. With the method of exhaustion, Archimedes approximated the area inside a circle by filling the circle with polygons of increasing area and number of sides. Plotinus argued that God was actually infinite. Augustine of Hippo asserted that not only was God infinite, but that God could comprehend actual infinity. Thomas Aquinas claimed that although God's power is infinite, God still cannot make an infinite being any more than he can make an unmade thing. Infinity has an incredibly rich history, but with limited time, we'll jump straight to Galileo Galilei. Galileo showed that wheels having different circumferences, when connected, traverse the same distance when revolved. He showed that the infinity of all natural numbers and the infinity of all the squares of the natural numbers were in fact the same, since they can be placed in a one-to-one correspondence with each other. Galileo claimed that actual infinity is not an inconsistent notion, but rather that it obeys different rules which we'd have to wait a few more hundred years for to be developed. But first came the development of calculus, in which Aristotle's views were further challenged. While the pioneers of calculus were largely uncomfortable with the idea of a line actually being composed of infinitely many points, they made great progress in assuming that a line is composed of infinitely many indivisibles, line segments of some incredibly small infinitesimal length, rather than a zero length. When faced with complicated equations involving infinitesimals, Isaac Newton and Gottfried Leibniz were able to divide by infinitesimals since they were non-zero, as well as ignore infinitesimals since they were near zero, allowing them to come up with incredibly simple methods for calculating derivatives and integrals. But some were uncomfortable with the loose treatment of infinitesimals. Bishop Berkeley called them the ghosts of departed quantities. And there were paradoxes. Consider this car, whose position is described by the function t cubed. The derivative of this function at t equals 0 is exactly 0. So is the car initially at rest? If so, when does it start moving? Several mathematicians tried to prove the soundness of using infinitesimals, but it would not be until 150 years later when, due to the work of Augustin Louis Cauchy and Karl Weierstrass, a way was finally found to place calculus on a firm and rigorous foundation without requiring infinitesimally small quantities. Rather than being an actual number, infinitesimals were just a label for something that had no fixed value, but had the potential to get smaller and smaller while never actually reaching zero. One might argue that calculus was made rigorous by basing it on potential infinity. But that's not quite the case, since the core objects of calculus remained the real numbers, and the real numbers are inseparably linked with actual infinity. For one thing, the decimal representation of the real numbers requires infinitely many digits. But when Georg Cantor introduced the world to set theory and the modern notions of actual infinity, Aristotle's potential infinity was put to rest. Aristotle had argued that a line is not actually composed of infinitely many points. In essence, that a one is not made of a many. But as Cantor said himself, a set is a many that allows itself to be thought of as a one. Aristotle and Cantor's views were in direct opposition to each other, and Cantor provided compelling arguments in support of his position. He assumed the existence of just one actual infinity, and from that assumption emerged countless of other actual infinities, a hierarchy of cardinal numbers and ordinal numbers, and most importantly, a theory which could be used as a foundational basis for mathematics. But it was not so easy for Cantor. He faced fierce opposition from many of his contemporaries, most notably Leopold Kronecker, who began an all-out campaign to discredit Cantor and obstruct Cantor's papers from getting published. Henri Poincaré called set theory an illness that was afflicting mathematics, of which it would eventually be cured. Nevertheless, within 10 years of Cantor's death, it was already commonplace that every mathematical object could be represented by a set. David Hilbert once said that no one shall drive us from the paradise which Cantor has created for us. But set theory was not free of paradoxes. The most famous paradox was Russell's paradox, which can be told as follows. The barber is the one who shaves all those, and only those, who do not shave themselves. The question is, does the barber shave himself? The contradictory state of the barber, well, its set theory equivalent, was seen as disastrous, since this seemingly innocuous contradiction would destroy the conventional meaning of truth and falsity. And given that set theory was used as the foundational basis for mathematics, Russell's paradox threatened the foundations of mathematics. It was not until Ernst Zermelo and Abraham Fraenkel proposed an axiomatization of set theory that avoided the paradoxes of Cantor's naive set theory. This axiomatic system, called ZFC, guarantees the existence of actual infinity, and it has remained the canonical axiomatic set theory at the foundation of mathematics to the present day. So have we arrived at the final destination? Is ZFC the proper foundational basis for mathematics? I suppose it depends on whether ZFC is consistent. But Kurt Gödel proved that an axiomatic system like ZFC can prove its own consistency only if it's inconsistent. So if ZFC is inconsistent, a proof of that inconsistency would be a monumental discovery, as it would create work for generations of mathematicians. But ZFC has been around for 100 years, and as of yet, nobody has uncovered an inconsistency with it. The absence of such a proof is not conclusive evidence of consistency, but it certainly is pointing in that direction. And if ZFC is consistent, if it is the proper foundational basis for mathematics, well, we will never know for sure.